Okay, so if collisions happen a lot, how do we handle collisions? So even with a perfect hash function, you're still going to get quite a few collisions. So we should handle them carefully. Let's talk about two common methods for resolving collisions. These are going to be sort of related to how Python did it before, and you'll see sort of aspects of both of them come out. But these are sort of your canonical academic things to talk about. We've got one called separate chaining. We've got one called open addressing. In practice, we use something similar to these, but it's sort of a combination of the two and with some additional intelligence built into it. So let's talk about separate chaining first. In separate chaining, we basically have a bunch of linked lists, which already makes me sad. I hate linked lists. They have a few use cases. I would not say that this is a prime use case of a linked list. Still, it's worth talking about because it's worth talking about why you might not necessarily want to do a pure separate chaining or maybe some sort of combination. So how does this work? Let's say we insert the object A. It gives us some value like this. You take it mod the size of your array. So in here is going to be 5. When you take it mod 5, maybe you get a 1. So you're going to insert that at the head of the linked list. Let's insert a second object. Take it mod 5. You're going to get 0. You insert that at the head of the 0 list. And try a third item. Take it mod 5. We're going to get 1 again. Where do you think we should put this value? Well, you've got really two choices here. You could put it at the head of this linked list or the tail of this linked list. I guess you could also put it somewhere else, but in separate chaining, those are the two choices. And we'll default to just putting them always at the head of the list. So why the head of the list? There's a couple of reasons why. It's the most efficient. So, we don't have to navigate down this entire list to put it at the end, which is how a linked list normally works. Unless it's a doubly linked list and you've got a pointer to the tail. There's some caveats here. But another reason we put it at the head of the linked list is this idea of the most frequently used piece of data is also the most likely to be used again in the near future. There's a specific name for that I don't recall off the top of my head. It's something we'll come back to in the next set of lecture slides. But since the C is the most recently inserted, we're going to put it where it's most easily accessible as well. All right, let's put in a couple more elements. We put in a D. That value mod 5 is 4, so we put the D there. One more item. And we put that one at the head of the one linked list again. So that is separate chaining. There's really no more to it than that. The second method we'll look at here is called open addressing. And instead of each of these being a linked list, each one is just a single individual bucket, and we handle collisions by just picking a different bucket. So now you can think of your hash functions as specifying a sequence, where maybe you put it in the first slot, and then the sequence is just to try subsequent slots to see if it can go in any of those. And that is called linear probing, when you just try the next available slot. So again, we'll put A in there. It maps to 1. Maybe we have a collision with B. It also maps to 1. What we do with open addressing with linear probing is we just add 1 to the hash function, which just means try the next available bucket. And if it couldn't go there, and we try to put a C, it couldn't go there, it'll just go into the next slot down below. So that's linear probing, and I want you to think about potential problems with linear probing before we move on. So what could go wrong here? I guess not necessarily wrong, but what could make this less than optimal or less than ideal? Well, it turns out if you use linear probing, you end up having blocks where you have collisions, and then you just put it at the next spot, and now you just increase the size of that block. So this usually will lead to clusters, which means you just have more and more collisions because you have these sort of contiguous spots in the array where nothing can go, and they all have to sort of follow this linear sequence. So that leads us to the next thing to discuss here, which is called double hashing, which breaks up this idea of having clustering. It requires two hash functions. You call the first function to get an index, and then you call the second function on a collision to get an offset. And then you add the offset to the index. If you have another collision, then you just try the offset again. So let's put A in there. B maps to the same spot. But now you just call two separate hash functions, still modify the bucket size, or sorry, the number of buckets, and that gives you a brand new number that's not just a linear probe. So the B would go all the way down here. If there was something there, you would just call this hash function again, which would, cycle you somewhere else up in the array. So those are our two methods for, our two sort of baseline methods for handling collisions. Now let's talk, before we move on, about how those compare to the Python dictionaries that we saw before and how they were, even somewhat recently. So the dictionary I showed you at the very beginning of the set of lecture, videos, was just for Python versions 3.6 and newer. So that's not been that old. So like, I think Python 3.6 came around, I don't know, 2018-ish. That's probably something I should look up and put on this slide, but it's not been around that long. So what did we have before that? So here is what the old version looked like. So in Python code, you might write something like this. So here's your key Timmy, here's your key Barry, here's your key Guido, and then the values you would store would be red, green, and blue. So what did that look like? Here is what your underlying C array looks like underneath. So take a look at this and see if you can see what kind of hash function collision detection, what kind of collision handling this resembles most out of the two that we just discussed. So it's not easy to see, I'll admit, from this example, but this turns out to be very similar to open addressing with double hashing. So why do I say this looks like open addressing? Well, if you notice, the things I'm storing in here are the hash value itself, the key, and the value. There's no like linked list here. There's no structure here that would indicate some sort of linked list. So it's open addressing, and there's no way to tell from this example that it's double hashing. But it uses double hashing to prevent that idea that I mentioned before with clustering. So this was what Python used for the longest time. And newer versions now seem like they've added some extra complexity for no good reason. So this is what it looks like now. We've got that indices table and an entries table. So why do we have these? Well, the biggest difference here is before we were wasting a lot of space. So for every empty space, we were wasting 3 pointers worth of information. So we had, or 3, I guess you could call them 64-bit ints worth of information. So we have the hash value here. We have a pointer to the key and a pointer to the value. Now when there are empty spots, it's just indicated by sort of a 0. It takes up a lot less space to say there's nothing in these spots. So if you notice, this 1 maps to this one, this 0 maps to this one, and this 2 maps to this one. So the same sort of structural information is available here as it is in the indices array. It's just that the data is now stored in an entirely separate array that you could think of as having no gaps in it, so we're not wasting any data. So why do we do this? It uses about 30% to 95% less memory depending on your particular application. Resizing the hash table only changes the value of the indices. So this is not something we've just discussed before. So let's say your array originally had, let's say 1, 2, 3, 4, 5, 6, 7, 8 slots. If you run out of space in that, then you double it to maybe 16 slots, and you have to copy all of this information over to the new one. Whereas this one, you don't have to do any copying of this into the new array. You can just sort of make this a dynamic array and continually add to the end of it. So there's less copying going on. And it has better cache utilization. So, that's something I'll star and we'll talk about in the next set of lecture slides.